All right, so in this new playlist, NLP in Python, I want to talk about some of the steps that you need to learn in order to implement very complex NLP projects, such as very advanced parsing methods and translations and complex tasks, which is built up on a very simple task, NLP tasks. So I start from very, very simple prerequisites for NLP, which is working with the pre-trained models and just using them because they're already trained, and we want to use them either as an embedding, as a for example, learning. And so the first lecture is about using pre-trained models in transformers for Bert representation. As you know, transformer architectures, those encoder-decoder architectures are very popular, but still old school LSTM. I love old school LSTM, GRU, by LSTM, by GRU, and those old technology, because they are more scalable. Transformers have their own problems because, the length of them are fixed, 512 tokens, I guess, and they are very, very expensive because, look, for each of them, you need keys, values, and queries, and then the matrices of them. And so for each token, and so it becomes n squared, and the computational complexity grows. And that's why we still love BioSim. Okay, for this lecture, assume that this has no problem, and we can use transformers in this lecture for Bert representation, because sometimes we just use the encoder of that transformer architecture, and we have trained it and for the Bert model, and then we can use it for our tasks such as translation. For any downstream task, first you need the embedding. And the first thing is you should install these transformers. And for example, this one is for sentence piece. And so as I said, like any other neural network, the transformers also can't process the raw input text directly. Hence, it needs to be pre-processed into a form that the model can make sense of. So this is what tokenization, because the computer doesn't understand the words, so we tokenize it. And then the text is converted into numbers. For example, index 21, index 35. And so these numbers can be understood because each number we can know, for example, which index of, for example, glove model is that, and we can find the vector embedding for that. But we don't use glove in this lecture. We are just using the pre-trained Bert model, and this is the checkpoint. This tilt Bert base, very, very, very simple, very light one. Uncased, and it is fine-tuned SST to English. And this is a tokenizer. We can see tokenizer outputs. It outputs a tensor, the tokenizer. We can see it as like this example, that the output of the tokenizer is like this. As you know, the first sentence, human mind is a Markov chain. This is what I believe. Is it needs lots of zeros. Why? Because it is filling it with some pads in order to make all the sentences, because all of sentences are not equal. For example, the first one is short, so we should pad it with the rest. The rest of them should be padded. The second sentence is a bit longer, like we should pay attention at right time and at right location, the second sentence, and we need some pads. And for example, the last sentence is a very long sentence, so we don't even need a padding to complete. And so that's why we use this to create some kinds of batches, and then so this is the thing that we need to do. So the input of the tokenizer is just the sentence, the text, the raw inputs. And don't forget that the tokenizer is coming from auto tokenizer, from transformers. So we get it from the pre-trained models, the checkpoint that I said. So it is from transformer. And then we use this tokenizer so we feed in the text, these raw inputs. And so it has just three sentences. And it gives you the tokens. So this is the index of, for example, human is 101. For example, mind is 2529. And then we are talking about this transformers library. So for any input to the model, we will retrieve a high-dimensional vector representing contextual understanding of that input by the transformer model. So when you are using the auto model, you can use from pre-trained models so that you have a model. So if you give some input, for example, your input could be this, then the output is 3 sentences. Each sentence has 18 tokens. And then we have 768 dimensions for each token. So that's why it is represented by a tensor. So the first one is batch size, the number of sequences. This one, they use just 3 sentences. And sequence length, the length of each sequence. For example, that all sequences are filled with pad in order to create 18 token for each sentence. So even if a sentence has just 8 tokens, we add 10 more pads in order to create 18 tokens, because we are fixing these 18 tokens for each sentence. And for each of these tokens, we have a vector, but it could be long. It could be 768 times 1. Of course, in the world of word embedding, this is still very small. And so this is the output of the model. So if you give a text, you understand the outputs, and you get the last hidden state, that shape. For example, even the last hidden state, the shape of that is enough for us. And so you see that this is very beautiful. And model using transformers library. So we can get the model directly from the checkpoint by using different class types of auto model. So we have 3 different classes. The first one is sequence classification. And the second one is causal language model. And if you're not familiar with causal LM of this, you can look at this. So the task of predicting the token after a sequence of token is known as causal language model. In this case, The model is just concerned with the left context, tokens on the left of the mask. So we have some tokens and suddenly you have a mask. You don't know. Then using these, it understands what is the next token in this sentence. And so this is kind of language model. The third, let's say, model is auto model for question answering. Question answering is a big topic. I've covered it with some of my lectures in the conversational AI playlist and some of my lectures in question generation. And I have another playlist, question answering. I have another playlist, semantic parsing. So it's very complex because we are talking about different things: question decomposition, question answering, question generation, and all of them are connected to each other. But sometimes you are not familiar with this topic. That's why you just use this model in your company, because you have limited time, so you cannot do research. You don't have time for research. That's why I use this naive approach, which is very simple. You just give the context, give it the context, the question, the context, and so you give it to this model, and the output is the answer of the question. So you train it. The reason that I don't like this architecture is just because it is not learning. It is like my niece, who is 4 years old. She's just imitating what big people say, whatever I say. For example, what a big guy is saying. She is not understanding it. So memorizing and imitating is different from understanding. That's why these models are just copying what is given to it, what is training data. It's most of the time overfitting that, which is terrible. So that's why this is not good for big companies like Salesforce. And that's why you need to do research and watch some of my playlist about question answering, question generation, question decomposition, and semantic parsing. So this is the example. You can find it in my GitHub. This is my ID, and this is the repository that you need to know for the first lecture. That this is this lecture. We are just using embedding, and this is the code. So first we import it, and then this is the checkpoint, as I said. Then we just need, but here we just need auto model for sequence classification, because we want to know the sentiment of this sentence. For example, I hate Putin since he has killed many innocent people. So this is just a negative. Its sentiment is negative, and that's why it has. So if you give the softmax, the logits are just numbers. You just need to normalize it and scale it in order to receive the outputs. But the output is just, for example, the probability of this one is very high. So, and we know that the first one is negative. So the probability of being negative is very high. And the second sentence, you see the second sentence, ancient Persian history shows beautiful friendship between Jewish people and Persians. And so it is very, very positive. So it's around 1. So 9.99, so it's positive. But the third sentence, I'm not sure if I like coffee more than tea. So it's not, so it should be 0.5, I guess, because we don't know if he likes it or dislike it or hate it or love it. So that, but you see, the problem is that because the model is imitating, it's just so this is a problem. This is a big error because it's not understanding. That's why your probability is almost 1. It's very negative. But this sentence is really not negative. It's just saying I'm not sure. And this is if you want to know the labels, you just need to know the ID2 label to see, for example, for ID0, it is negative. For ID1, it is. So it's just two-class classification. And the codes are available here. And I think that's it.